All right. How did you do on that quiz? Did it seem easy? Were you able to pick it out? Let's take a quick view back at it, right? So what's the one thing here that's predictive? Big hint, it has the word predict in it. It's D. Okay? So that's the machine learning-ish thing there. All right, so we're going to give you an overview now of machine learning. So we're going to break it up into 4 parts. Okay, first off, we have to partition the data that we've got into different chunks that we use for the machine learning process. And then we're going to do we're going to do we're going to absolutely do model selection. In many cases, you're going to do feature selection as well. Okay, and then we're going to assess the models. So the model selection, so that to be a little bit more clear as we add a little bit more detail, right? We have to break the data up into different parts to do different parts of the task. We have to pick the model we're going to use for the task, and sometimes we have to engineer the data we've got into particular kinds of features to make the learning task easier. And then all that just needs to be trained and use the process. And at the end, we have to use ways to assess whether the model did any good at its job. Okay? So let's dive deeper now that I've blah-blahed about the top level. So data partitioning. Typically in a task, we're going to get one data set dumped in our laps. And that data set is what we're going to have to use to create everything about the machine learning system. But we're not going to use all of it for every single part of the system. Okay? So here's our chunk of data that we get dropped in our laps. We've downloaded all the coronavirus information up to September, or we've downloaded, IMDb's database of movie reviews. Okay, this is all the stuff we've got up through 2020. Okay, so in order to create our model, we need to split this data up into at least 2 parts and more likely 3. Okay, so if we're going to do any kind of model selection at all with the data, model selection or feature selection, we need to break the data up into training data and validation data. Okay, what is this? Well, training data is what we actually use to build the model. Okay, so we're going to take, generally you would say something like maybe 2/3 of the data or 3/4 of the data and throw it to the training data, and it gets used to create the actual model. The validation data is still from that same original data set, the big data dump we got, but it's not used in training the model. What we use it for is selecting different forms of the model or selecting different kinds of transformations of the data into these features. Okay? So we're going to get a little bit more into that detail right now, but I just want to say there's one last piece of the data set that you need to be aware of. Okay? So finally, we may need some test data. The test data is a completely new data set. It was never used for training. It was never used for validating. Okay, so typically what we may have to do is we may have to split this 3 different ways. We may have to take some of the data and set it aside for training, some of the data set it aside for validating, and some set aside for testing. And once again, the training data is building the model. Okay. The validation data is for fine-tuning the model, twiddling the parameters back and forth to try to get it the best possible model. Okay, and then once we have the best possible model, we use the test data to find out, is this any good? And for us to know if it's any good, it has to be a completely independent chunk of data that didn't get used in either of these 2. Okay? let's go deeper in. Let's talk about what would happen if we had some model selection stuff going on, okay? We're going to try different forms of the model. Maybe this means different algorithms completely, or maybe this means we're going to twiddle the knobs on the parameters back and forth. And we're going to see on the parameters on the model of what happens if we turn the dial all the way up to 11, right? Or if we drop it down a little bit. Or maybe we even try different transformations of the data. Maybe the data that comes to us is height and weight, right? And we're trying to predict something health-wise, okay? We can feed in height separately and weight separately. Or if you're familiar with the construct called body mass index, BMI, BMI is just a combination of height and weight. There's a little mathematical formula. You plug in height and you plug in weight, and out comes BMI. So we might get very different algorithm performance at our prediction task if we give it height and weight separately versus if we give it BMI as an input, which is a combo of height and weight. So that's what I mean by different data features. We might re-engineer the data we have to make it easier to learn the setup. Okay, any of these are part of the model selection process. Okay, so we're going to try different things here. We're going to try, twiddling the knobs, or we're going to try a new model, or we're going to try different remix of the data features. Okay, we're going to run them through the system. How are we going to do that? Well, so we're going to train it on the training data, right? We've split up our data set into the 3 parts. So we're going to train all 3 of these instances of the machine learning system on the same data. And then we're going to try the trained setups, these 3 trained setups, we're going to try it on the validation data. And each one of those different models will get a different performance level on the validation data. And we pick the one which does the best, and we say, hey, this is our model. This is the best we can do with this setup. Okay, and finally we take our best model and we run it again. We train it up again from scratch using all the data, and then we test it on the test set. Okay, because the test set never went through, the test set data was never in the training or the validation. It's completely new data, and it gives us some confidence that if we do well on the testing data, we are able to generalize to brand new situations. Okay, so we hold out some of our data from elections in 2016. It never gets used for training, this data, and we test against it so that we know what we're likely to encounter when we're trying to predict 2020. All right, so feature selection, as I mentioned, is about engineering the features of the data, right? Say your data set includes all kinds of variables, all kinds of columns, right? If one of them is elephant height, it's probably not going to help predict the election. Okay, but things that are more election-based might be. But your data has all these columns, including the elephant height. Am I going to draw an elephant here? This could be bad, people. Okay, there's my elephant. Okay, so, right, you have all these columns. What are you going to do? Well, you could, in the case of elephant height, very easily weed it out. You can go look at it and go, no. All right? But more likely, in a more realistic situation, it's not going to be like that. You're not going to be able to just look at something and say, remove it. You're going to have lots of variables. Some of them will be helpful, some will not. So you're going to let a system perhaps automatically try to select which variables are useful. And that's where we go back to what we were talking about just a second ago with the validation. Okay, we use the validation cycle, trying different subsets of these variables and seeing which ones let us predict the best. Okay. Finally, it is important to note correlation and causation, not the same thing. These variables can be used to predict, right? They can be accurate for prediction. It doesn't mean they caused it. Let me give you an example. Age prediction is something that I've done in my own research. Okay, so we have a bunch of measurements of people's gene expressions, or, you know, their grip strength is actually a good predictor of their age, right? Stuff like that. There are various measurements that are made in doctor's office and in laboratories, and we can use those to try to predict somebody's age. Okay, one of the measurements you can do is the elasticity of the skin, right? Pinch and let go. It just flings itself back into place. On me, it's, you know, not quite so fast. And on my mother, she pulls it out to here and it comes back in next week, right? That elasticity change predicts age very, very well. Okay? Why? Is it because the change of your skin elasticity is aging? No. Why does it? Does anybody have an idea? Anybody? Yeah, Jeff Lebowski, second row. Okay, dude. Well, I mean, it is the case that aging people do have messed up skin, but why? Why, Lebowski? Okay, so let me help you out a second, and please don't bring white Russians to class anymore. That's not cool, dude. So aging process is going to cause a lot of changes in the body, and some of those include the cells that repair the skin start to degrade, and so they stop repairing the skin. Another thing that happens is sun damage. The older you are, you've probably spent more time in the sun in total. So those two things together are not aging, they're effects of aging, right? And so they're effects of aging, which are good for predicting age, but they're not the aging itself, all right? So that's what we mean when causality is not the same thing as what we're predicting from. We can predict from things that have nothing to do with the actual process, but they're caused by the process we're interested in. All right. So let's talk about how we're going to actually do this. There are two big chunks of machine learning, right? There's the supervised world and the unsupervised world. In the supervised world, somebody came through and took this data and they put X's and O's on it, right? We're just saying that whatever these data here are here, this is class 1 and this is class 2, okay? Maybe these are, people who got sick, and these are people who stayed healthy. All right, so from these measurements, can we predict whether they got sick or stayed healthy? That's supervised learning. So somebody did the labeling for you, which helps tremendously. Now, the other version of this is unsupervised learning. There are no labels. The world is an unlabeled place in general. So what these kinds of algorithms do is they have built into the algorithm itself a way of looking at similarity, right? And saying these things are more similar to each other than those things, okay? So we're going to say here are two groups of things. All right, once you break it up a little bit further, we can say that in supervised learning, there are two subcategories. There's classification, which is, as I kind of alluded to a second ago, it's sick versus healthy. And the algorithm learns to draw a line that separates the sick and the healthy. Okay? And then when it gets new data point in here, so this green is my new data point, okay, it can use that line it created to predict whether somebody will be sick or healthy. Now, regression is another version of this where instead of being at trying to say it's one of two things, sick or healthy, what we're after is a continuous variable. We're after a prediction. Oh, look, my video stopped. That's awesome. All right. So we're gonna get after, like, you know, what is somebody's age? Somebody's age is not just sick or healthy. Somebody's age is not a discrete number of things. It's a continuous real number. And so given some measurements along here, you know, what do I think somebody's age would be over here? Right? And finally, in unsupervised learning, what they're doing is they're creating clusters, okay? And those can be used to automatically identify the structure in the data. All right. Quick little quiz. Which parts of the data are used for model training, model feature selection, and quantifying generalization performance? I'll let you get after the Google form and have a little quiz while I take a break and switch my camera battery. Hopefully that's all it is. See you soon.